and welcome to L'Hopital's rule, which is 7.7 in our current textbook. L'Hopital's rule starts off with, let f and g be functions that are differentiable. That just means you can find their derivative. Assume that the derivative of g is not equal to 0. Now suppose the limit of f of x is 0 and the limit of g of x is equal to 0. Then the limit of f of x over g of x is equal to the limit of its derivative of f over the derivative of g. Now what we're going to do is we're going to look at limits, and the most useful, or the most you're going to see the type, is this guy right here. So what we're doing is we're going to be looking at fractions. We're going to look at the limit as x approaches anything. If when I find my limit, I get 0 on top, 0 on the bottom, infinity on top, infinity on the bottom, those are forms that fit into L'Hopital's rule. Now, in the past, if we get 0 divided by 0, then we have to look for opportunities to factor, multiply by the conjugate, do some kind of algebraic simplification. And a lot of times that simplification can be quite exciting. With L'Hopital's rule just says you got something that looks like this. If you get the top equaling 0 and the bottom equaling 0, that fits into this perfect L'Hopital's form. So just take the derivative of the top, the derivative of the bottom, and then try it again. Wherever that limit is going, that's where the original function is going. Now we're going to discuss all of these different forms. So basically, if we plug the numbers in and we get 0 divided by 0, infinity over infinity, because that's not 1, 0 times infinity, 0 to the 0th power, infinity to the 0th power, 1 to the infinity power, and infinity minus infinity. Any of those forms, we know we can use L'Hopital's rule, which means we're going to take the derivative and then try that limit again. So let's see what this is going to look like. All right, so these are going to be the most basic examples, the examples that we're going to see the most. All right, so what we do is we put pi over 2 in here. So we have 1 minus the sine of pi over 2 divided by the cosine of pi over 2. Well, that's going to give me sine of pi over 2 is 1. Cosine of pi over 2 is 0. Oh, we get 1 minus 1, which is 0, over 0. So this is what tells us L'Hopital's rule is going to apply. So what we want to do, L'Hopital, okay, I shorten it, of course. We have to write L'Hopital's. So what we're going to do, and I might want to write L'Hop so that looks a little better. There you go. So we're going to now apply L'Hopital's rule, which means we're going to take the derivative of the top, the derivative of the bottom, and then we're going to try this limit thing again. Now notice this is not going to be a quotient rule. You are literally treating the top function as a separate function from the bottom function. So we are literally going to do f prime over g prime, which makes it even easier. Okay, so if we do that, the derivative of 1 minus sine is negative cosine. The derivative of cosine is negative sine. Now when we put that pi over 2 in there, we get negative 0, or just plain 0, over 1, which is equal to 0, which is not undefined. It's an honest-to-goodness answer that is valid. So by L'Hopital's rule, if the derivative of the top over the derivative of the bottom, if that limit exists and goes to 0, therefore the original statement, the limit as x approaches pi over 2 of the original, that also goes to 0. Okay? Now we don't have to get as intense at showing this. We're going to be plugging those values in, and I'm just going to put a little 0 over 0 or infinity over infinity, and then we're going to go right to the derivative. plug that value in again. Wherever that derivative is headed, that's where the original function is headed. Now remember, this only works if f and g are differentiable and g prime, the derivative of g, is not equal to 0. So let's do another. And seeing how we're talking about L'Hopital's rule, let's stick with French and do un autre. Look at me, bilingual math, woo! All right, no, we'll stick to English, sorry about that. Okay, so when I put 2 in here, I'm going to get 2 to the third, 8, minus 2 times 2 to the second, which is 8, so 8 minus 8, plus 2 minus 2, I get 0 on top. When I plug 2 into the bottom, I get 0. This is going to tell me L'Hopital's rule. So I'm going to, wow, I'm just slapping that limit on there. I'm going to take the derivative of the top. Well, the derivative of x to the third minus 2x squared plus x minus 2 is 3x squared minus 4x plus 1 all over the derivative of the bottom, which is 1. Now when I put that 2 in there, I'm going to get 3 times 2 squared minus 4 times 2 plus 1, all divided by 1. That gives me 5. So if this is where the derivative's going, therefore the original statement also goes to 5. Okay, so that's not so bad. Let's do another one. So if I put 0, e to the 0, that's 1. Minus 1, ooh, I get 0. 0 in the bottom. Now I'm ready to do L'Hopital's rule. Okay, so the derivative of e to the x is e to the x. The derivative of x is 1. That automatically tells me I'm going to get finished. Ooh. All right, so now when I put 0 back in there, e to the 0th is 1. Divided by 1 is 1. Therefore, my original limit by L'Hopital's equals 1. So we don't have to try to get algebra to get this to simplify, because this would be quite difficult if we didn't have our calculator. It's kind of hard to think about what would I multiply by to simplify. Very, very difficult. Okay, so we are continuing on with the magic. Okay. So once again, we're going to put 0 in. Well, the cosine of 0 is 1, so we get 1 minus 1, which is 0. 0 squared, 0. Okay, so now we know that L'Hopital's rule is going to apply. The derivative of negative cosine is positive sine. The derivative of x squared is 2x. Okay, now when we put 0 in, the sine of 0 is 0. 2 times 0 is 0. What do you think this means? Oh, if you guessed, hey, I bet we can do L'Hopital's rule again, you would be very correct. So we can do L'Hopital's rule again. It's kind of like integration by parts. We can keep doing this until we don't need to keep doing this. So we're going to take the derivative of sine, which is cosine. The derivative of 2x is 2. Oh, looks like we're going to be done because there's no way I'm getting 0 on the bottom. Put 0 in there, I get 1/2. Okay, so therefore, by L'Hopital's, okay, the limit as x approaches 0 of 1 minus cosine of x over x squared must also equal 1/2. So somewhere you've got to let them know that you're looking at that 0 over 0 form, and then somewhere, therefore by L'Hopital's, somewhere you've got to mention that L'Hopital's rule is applying here. Okay, so let's see what magic can happen on this problem. If I put infinity in here, e to the infinitieth power, okay, e to a big number is going to be a big number. Big number squared, big number. Ooh, so this is the first time we've had our infinity over infinity. So we are going to apply L'Hopital's rule. So somewhere let them know you're applying L'Hopital's rule. The derivative of e to the x is e to the x. The derivative of x squared is 2x, and it looks like we get to do it again. Make sure you're letting them know why you're doing L'Hopital's rule, and that's because we've got infinity over infinity. The derivative of e to the x is still e to the x. The derivative of 2x is 2. So when I put in my infinity this time, I get infinity over 2. Okay, this is not one of L'Hopital's rules or forms. That's going to be infinity. Well, remember, sometimes limits just don't exist. If they have no bound, which is what we have here, if the left-sided limit doesn't equal the right-sided limit, we got a problem. If it oscillates, we got a problem. So just because we have L'Hopital's rule doesn't mean everything is going to work out. Sometimes bad limits just happen. So this limit does not exist, therefore the original limit just doesn't exist. Now, as I'm looking at these, remember how I showed you the 0 over 0, the infinity over infinity, and I said those forms you're going to work with more? Well, there's a reason why we're going to be working with those more. When we look at our next form that we're going to talk about, the 0 times infinity, notice that's not a fraction anymore. Now what we want to do to solve this, we are going to convert it into a fraction because we really want to get 0 over 0 or infinity of some kind over infinity of some kind. It doesn't matter if it's positive, negative, negative, positive, 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 negative, negative. Okay, so we not only will see this more, we will be creating this L'Hopital form. Okay, and please remember that infinity, think about it as a time frame. Okay, a lot of people will look at infinity over infinity and go, well, why isn't that 1? Okay, well, that would be like I'm getting in a car and driving to California, you're getting in a car and driving to California. You're saying that we will always be side by side the entire time. That's not going to happen. I'm going to be ahead, you're going to be behind because I drive like a maniac. Okay, it's like a destination, a rate of speed, so to speak. Just because you're getting to infinity doesn't mean you're getting there at the same speed as this little guy's getting to infinity. So that's why infinity divided by infinity is not equal to 1. Okay, so when we're looking at this product, we are going to choose to take one of them and put it on the bottom and flip it over. Okay, so when you divide by the reciprocal, think about it. If you had this statement and you flip and multiply, you're going to get the original statement. So it's like we're taking that fraction backwards. Okay, so when we're looking at this, we're always going to look at one that we would rather flip over than the other. Natural log is not really something we'd like to flip over. If we have trig functions, we'll want to flip those over because you have reciprocal identities. So the first thing we have to do is show that we have one of these forms converted into the preferred form. So we are approaching 0 from the right side. Well, if I put 0 in there, that's going to give me 0. If I approach the natural log of x from the right side of 0, that's going to give me negative infinity. Okay, because we're going down, down, down. So that fits into L'Hopital's form, which means we are going to flip one of them over and divide by it. I'm going to flip the x over. So I take the reciprocal and put it on the bottom. So this guy right here, I take his reciprocal and I put it on the bottom, because if I flipped and multiplied back, I would end up with the same thing. Now when I look at this, I have my negative infinity on top. 1 over x, well, as x gets very, 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 very small, this fraction gets very, 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 very big. And since I'm on the positive side of 0, that's going to go to positive infinity. Now we have the perfect L'Hopital's form. Okay, so we're going to take the derivative of the top, the derivative of the bottom, and see what magic we can make. Okay, the derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. So if we flip and multiply, remember when we're writing out free response problems, we must write out our work. So that's going to be negative x squared over 1. So this little guy just turns out to be the limit as x approaches 0 from the right of negative x. Well, if I put 0 in there, I'm going to get 0. Please do not put negative 0. Oh my goodness, that would be so embarrassing. Therefore, if this is what the limit equals here, then this is what the regular limit equals by L'Hopital's. So you might want to put by L'Hopital's x natural log of x equals 0. And make sure you put this last step here, because it seems almost rude if you don't, because they're asking you to find the limit as x approaches 0 from the right side of x natural log of x, and then all of a sudden you say, okay, well the limit as x approaches 0 from the right side of negative x is 0. It's almost like you're not answering the question. So you need to show them, hey, this is the form that fits into L'Hopital's. I'm going to rewrite it into the preferred form. Now I'm going to perform L'Hopital's. By that L'Hopital's rule, I know that this limit is going to go to the same place as my limit. Okay, so we just have to make sure we are letting them know why this equals 0 means this guy equals 0. Okay, I'd like for you to try this one. Okay, now when we're flipping one of these guys, let's try to flip this one. Okay, you know you've got the right answer if you get 0. Okay, so try this one. Okay, we'll go through it in class if you need it. So remember, you're going to flip tangent over. All right, so looking at a new form, infinity minus infinity. So you're looking at 2 fractions probably, or 2 terms. Going to get a least common denominator and see if you can get that alternate form or that preferred form of L'Hopital's. So if I do this, if I put 0 in as I'm approaching it to the right side, sure enough, I get infinity minus infinity. So I'm going to get a common denominator and see what happens from there. I'm going to use x sine of x. This guy was missing sine of x. This guy was missing x. When I plug 0 in, sure enough, I get 0 over 0. Okay. So I need to find the derivative. So the derivative of sine is cosine minus 1 over, now when I find the derivative at the bottom, I do have to do a product rule. So the derivative of x times sine as is plus the derivative of sine times x as is. I'm going to plug that 0 back in there. Okay, so I get 0 on top because cosine of 0 is 1. 1 minus 1 is 0. And then I get 0 plus 0. I get 0 again, so I get to use L'Hopital's rule again. Okay, the derivative of cosine is negative sine. The derivative of sine is cosine. Then I have this product rule again. So the derivative of x is 1 times cosine as is, plus the derivative of cosine, which is negative sine, times x as is. So negative x sine of x. When I put 0 in again, I'm going to get the sine of 0, still 0. I get the cosine of 0, which is 1. Again, I've got it. And then I get my minus 0. So I get 0 over 2, which is just 0. Okay. And therefore, by L'Hopital's rule, the original has to equal 0. Okay? All right, so looking at this little guy here, I've got, as I'm approaching 0, that bottom gets bigger, or gets smaller, 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 so that's going to infinity. Same thing here. This is getting smaller, 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 so it's going to infinity. You got the minus sign there. So we know we can get a common denominator. We're going to use x, e to the x. So you can see a lot of product rules coming your way. That's going to give you e to the x minus 1 minus x. Okay, and then we are ready to, oh, oopsie, there we go. Sorry about that. Okay, so we've got x, e to the x minus 1. So we take the derivative of the top, which is going to be e to the x. The derivative of 1 is 0. The derivative of negative x is negative 1. And then I've got my handy little product rule. So the derivative of x is 1 times e to the x minus 1, as is. Okay. And then plus the derivative of e to the x is x e to the x. Yep. And then we need to put our zeros in again. Well, if we put our 0 in, e to the 0 is 1, minus 1 is 0. Okay. And then, oh, I forgot to do that up there. Well, that is 1 minus 1 minus 0 is 0. 0 times anything is 0. Okay. And then on the bottom, I get 1 minus 1 plus 0. We get to do the whole party again. Make sure that you go back, if you forget, like I did up here, to put your 0 over 0 or infinity over infinity, because if you don't have one of those two, you can't use L'Hopital's rule. You would be done. Okay, so I've got e to the x on top. On the bottom, I have e to the x, and then I have another product rule, so I have e to the x plus x e to the x. When I put 0 in, I get 1 on top, so I know I'm going to be finished. I have no more L'Hopital's rule. I get 1 plus 1 plus 0, so I get 2. Therefore, by L'Hopital's rule, the limit as x approaches 0 of 1 over x minus 1 over e to the x minus 1 also equals 1/2. Okay. All right, we have one last form, and that one's possibly the most fun. And yes, I'm kidding when I say that. When you have the limit of a function and the power is a function, we can't have x's in both positions. Now, we've had problems with this setup before, because when you're taking the derivative, you can't have x's in the bottom and x's in the power. Okay, you can use the power rule, or you can be an exponential, but you can't be both. Now, the way we handled this with derivatives, exactly the same way we're going to handle it with limits. And that is, we're going to natural log both sides, so we can pull this power down in front. So we're going to let y equal what's inside the limit. So that's going to be our y. Well, I need that g of x to come down in front. So I'm going to natural log both sides so that g can come down in front. So we're right here. Well, we're taking the limit of this guy, okay, because see, we had that little limit, so now we're going to incorporate the limit. So I'm taking the limit of both sides. Now, when I find the limit of this guy, that's what the natural log of y is equal to. So we've got to e both sides so that I can find out what just y is equal to. Because what we want to know is just what the limit of f of x, g of x is equal to. So we natural log both sides, but then we have to e our answer to get back out of it. So let's see what that's going to look like live and in person. So basically, we're going to let y equal 1 plus 2x to the negative 3 divided by x power. I'm going to natural log both sides so I can pull that power down in front. Okay. And now I am ready to take the limit. So the limit as x approaches 0 of my natural log of y is equal to the limit as x approaches 0 of negative 3 over x, natural log of 1 plus 2x. Wow, that just morphed right out of there. Okay, So really what we have here on the right side is negative 3 natural log of 1 plus 2x all over x. So I end up with 1 plus 2 times 0, so that's 1. The natural log of 1 is 0. Then we have 0 on the bottom. So we're ready to jump right in and find the derivative. Okay. So the derivative of the top, that negative 3 is along for the ride, times 1 over what you're taking the log of, times the derivative of what you're taking the log of, which is 2, all over the derivative of the bottom. Okay. So if I clean that up a little bit, that's going to be negative 6 over 1 plus 2x. Okay. So if I put 0 in there, I'm going to get negative 6. Okay. Well, remember, that's what the natural log of y is equal to. So if the natural log of y is equal to negative 6, then y is equal to e to the negative 6. Okay? So therefore, don't forget that, oh yeah, therefore, by L'Hopital's, L'Hopital's, the limit as x approaches 0 of 1 plus 2x to the negative 3 over x power is equal to e to the negative 6th. Now you have to admit, if we didn't have L'Hopital's, how would you have ever come up with the answer to that limit without him? So L'Hopital's rule is going to be very important to us. I'll see you back in class.